Hello students, in this video we'll discuss the principal axis problem for a specific hyperbola. Let's consider the hyperbola two xy is equal to 1. Okay? Now of course we might ask the question, if the standard form of a hyperbola is x squared over a squared minus y squared over b squared is equal to 1, then how is this hyperbola? Then how is 2xy equal 1 a hyperbola? And this is where linear algebra comes in and saves us. I know that these hyperbolas over here have what shape over here? These have the shape x-axis, y-axis. They look like this over here. Like that. They have this sort of almost parabolic shape like that, but there's asymptotes, of course, like that. And of course, when y is equal to 0, these are the points A and negative A, right? And then these have these asymptotes over here, b over a. So there's an asymptote like that, an asymptote like that. And these asymptotes over here, these ones are sort of not exactly perpendicular, but of course, if a and b are equal to each other, then the asymptotes are perpendicular to each other, okay? So they're not necessarily perpendicular, but in this case, when a is equal to b, they are perpendicular, okay? Great. All right, so here's where linear algebra is going to come in and save us over here. So I'm going to make the observation that 2xy is really equal to what? Is equal to xy, then this matrix over here, 0, 1, 1, 0, and then this vector over here, xy. And we can easily check that, right? Because this is a what? This is a 2 by 1. This is a 1 by 2 rather, 1 row by 2 columns. And we're multiplying that by what? We're multiplying this 2, 1, 2. Get rid of that x over there. This is a 1 by 2. This is a 2 by 2, and this is a 2 by 1, so it's going to output a 2 by 1. So this is going to output x times y, and then a y, and then an x, like so. And that gives me a 2xy, okay? So what we have over here, so let's tie this up a little bit. This is going to be an x times y. It's just going to be an x times y, which is a what? It's a 1 by 2 matrix. Excellent. Okay. And so now the objective is that what I'm going to do is I'm going to diagonalize this matrix over here. So let's diagonalize that matrix. So if we diagonalize that matrix, let's find the let's call this matrix over here A. And I found the eigenvalues of the determinant of what? Of negative lambda, 1, 1, negative lambda equals 0. This becomes a lambda squared minus 1 is equal to 0. And then this is lambda is equal to plus minus 1 are my eigenvalues. And now let's check what the eigenvectors are. So when lambda is equal to 1, you're going to have this augmented matrix over here. You're going to have the matrix negative 1, 1, 0, 0, and then a 1, negative 1, 0. And when lambda is equal to negative 1, what augmented matrix are you going to have? You're going to have this augmented matrix. You're going to have when you're negative 1, you're going to be a 1, then a 1, then a 0, and then a 1, then a 1. Okay? So now we're in good shape because what we can do now is we actually can just write out exactly what this is. And I'm going to choose special vector. I'm going to normalize the eigenvectors over here. So I'm going to write that A is equal to what? I'm going to write that A is going to be a matrix of eigenvectors. So typically there's be like a 1 and a 1 over here. So I'm going to do a 1 over root 2, 1 over root 2, 1 over root 2. That would be an eigenvector over here for this guy over here, lambda 1. So this eigenvector over here is going to choose to be 1 over root 2, 1 over root 2. And then over here we can do negative 1 over root 2. We'll do negative 1 over root 2, 1 over root 2 for that eigenvector. So then we'll have another eigenvector over here. So we'll have a negative 1 over root 2, and then a 1 over root 2. That's my P. And then I have my diagonal matrix. I'm going to have a what? I'm going to have a 1 first, a 0, and then a negative 1. And then I have the inverse of this matrix. I'm going to call this matrix over here U, right? And then this over here is just going to be what? Since this is an orthogonal matrix, I'm just going to put a U transpose over here. So that's going to be a 1 over root 2, and then a negative 1 over root 2, and then a 1 over root 2, and then a 1 over root 2. That seems like an awful lot of work, but now what I'm going to do is I'm going to write this as u transpose, and we're just going to keep those as u and u transpose. Now what is u? U is rotation by 45 degrees, right? So u is a 45-degree rotation. Rotation by pi over 4 radians, or 45 degrees. Okay? And that tells us that my 2xy is equal to what? So our 2xy is really equal to x, y, then u, like that. And then my diagonal matrix over here, 1, 0, 0, negative 1. And then my u transpose over here times xy. Okay? So what we can do now is we can set x prime, y prime to be u transpose of xy, which tells me that x times y is equal to what? X times y is going to be equal to u transpose, just u, because it's a self-inverse, right? It's just going to be u x. In other words, this is a change of basis to rotation by 45 degrees, right? And so now what this tells me, if I call this x prime, y prime, this tells me that this is exactly equal to what? It's exactly equal going to be what? We're going to have what now? We're going to have this, this is like my x prime, y prime. I'm going to have x prime squared minus y prime squared. And so x prime squared minus y prime squared will be equal to what? Will be equal to 1. And now I know exactly in those rotated coordinates, I know that that's a 45-degree rotation of this standard hyperbola over here. So if I rotate that hyperbola by 45 degrees, what will we see? We're exactly going to see what? So this is a 45-degree rotation in my new coordinates. So if we're to plot this over here, what's going to happen? Here's my x prime and my y prime, my x and my y. And of course, x prime and y prime are these 45-degree angles over here. That's my first eigendirection. That's my major axis and my minor axis. In this case, the major and minor have the same, like that. And now I'm going to draw the hyperbolas on these axes over here. So I do a 45-degree rotation. So what's going to happen over here? I'm going to get something like this, like that, and like that. And so now I've seen that. I've just taken this hyperbola over here and I've just rotated it by 45 degrees. And so in fact, the standard thing that we see from calculus, I would say, oh, it looks like this as an asymptote of the x-axis and the y-axis. That follows from the fact that I've just taken these asymptotes over here and rotated them by 45 degrees. And so this asymptote over here becomes the x-axis, that becomes the y-axis. So my asymptotes have changed to y equals x and y equals negative x. And that proves that this x times y is equal to 1 is in fact a hyperbola. It's just in rotated coordinates. Thank you very much.